Hello, fellow pedestrians. Like we said in the previous video, um, what we are going to examine in this lecture are separable ODEs, meaning differential equations that can be split, can be written in the form y prime is equal to a function of x times another function of y, where y prime is nothing more than the first derivative of the y function with respect to its independent variable x. So let's jump straight into the first example. Y prime is equal to minus y squared, which is a non-linear differential equation of first order. This can be written as dy over dx is equal to minus y squared, and this can be separated, get the y's and x in the different sides of the equation, as dy over y squared is equal to minus dx. And here we can integrate its term, so this integral is just minus 1 over y is equal to, this is just x, so minus x plus a constant, and the y function we are looking for, that is the solution of this differential equation, is nothing more than 1 over x plus the constant. Of course, you can see we have a lot of freedom. This constant is not the same as this. There is a minus sign difference, but since it is a constant, we can use whatever sign we want, right? And the thing with differential equations to start with is that you can very easily, in any case that the differential equation is not very involved, you can very easily check that this a solution is indeed the solution of the differential equation. Here, if you differentiate with respect to x, you get that minus 1 over x plus squared, which is y prime, and this is indeed minus of y squared. So this is indeed a solution to the initial differential equation. Okay, example 2. xy prime plus y squared is equal to 0. Again, dy over dx is equal to minus y squared over x. We separate and integrate, so dy over y squared is minus dx over x. This is minus 1 over y equals minus ln of x plus a constant, so y is 1 over ln of x plus a constant. Again, with the this constant is different to this, but it's still a constant. Another example, a more evolved one. 2xy prime plus y squared minus 1 is equal to 0. This is written as dy over dx is equal to 1 minus y squared over 2x, and integrating and separating, dy over 1 minus y squared is equal to dx over 2x. Now, let's pause here for a moment and check what this integral can be. There is a common practice when you have a denominator that can be separated into multiple roots, and the common practice is, let's say you have something on the let's say a gamma on the numerator, and let's say you have x minus rho of n and x minus rho prime. Let's say this is not a derivative of m, this is just a different root of this. This can be separated into multiple fractions and can be written in a way that it will be much easier to solve the integral. And the common practice says that if you have a real root, this involves only real roots. If you have real roots of n multiplicity, you will get the same amount of fractions with constants on the numerator. So this could be written as a1 over x minus rho plus a2 over x minus rho squared all the way up to a n x minus r to the n, and this could be written in the same way as, let's say, b1 over x minus rho prime plus blah 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 all the way to bm of x minus rho to the m, and we'll see that using the specific example. Now this is the case if you have real roots. If you have complex conjugates as a solution to the second order equation, then what changes is that the numerator, instead of constant, all of these are constants that we are going to deduce, so we are able to split this denominator. In case of complex roots, instead of constants, we have exactly the same thing in the denominator with the same number of fractions for its multiplicity, but in the numerator we have something like this: a of x plus b, and x squared plus a x plus c. Okay, this is going to be this will have complex roots, but the numerator is going to be like that. So into our own example, 1 over 1 minus x squared is going to be written as 1 minus y 1 plus y, right? So we only have real roots. So for this root of multiplicity 1 we have just one constant, and for this we have another constant, and doing the math, which is a plus a y plus b minus by is equal to 1. This means that a plus b is equal to 1, and a minus b, because y is going to be 0, so because there is no y term here, so a and b are the same, and from this a is equal to b is equal to 1/2, right? So the integral is going to be written as 1/2 over 1 over 1 minus y plus 1 over 1 plus y dy is equal to dx over 2x. 1/2 and 1/2 goes away, yes, and we take the integrals, which are much more simpler than the previous one. So this is just minus ln of 1 minus y plus ln of 1 plus y is equal to ln of x plus a constant, which is, this can be rewritten as 1 plus y over 1 minus y is equal to ln of x plus a constant, and finally is equal to a constant times x, and this is written in its implicit form. And if you separate y and do the math, you will finally get that y of x is nothing more than x plus a constant, x minus a constant, right? And this pretty much sums up how we deal with differential equations of this form when you can separate x and y, and it is indeed the easiest form that one could find when dealing with differential equations. The thing is that every solution and every aspect that we're going to deal with, it always comes down to simpler solutions. So you could solving a second order differential equation, and after solving and solving, you will get down to maybe a separable or ODE. So it's very important to build from zero, so we will be able to tackle more different differential equations. Now, since this was a very short video, we can move on and check another kind of differential equations that one could stumble upon, which are called homogeneous, in the sense that the fraction y over x will have a constant order all over the D. It's easier to see it through examples. Let's say y prime is equal to x plus y over x, which can be written as 1 plus y over x. So the fraction y over x has the same power both for y and for x. In these cases, the transformation we are going to use is, let's say, we change the variable u to y over x, meaning that y is equal to ux, and differentiating y prime is equal to u prime x plus u. Okay, now this is the change of variable we're going to use when stumbling across such kinds of differential equations. So this is nothing more, this is y prime, so we write it with respect to u, so u prime x plus u is equal to 1 plus u. U and u goes away, and what do we have here? We have a separable differential equation of the form du dx is equal 1 over x, meaning that the integral of du is the integral of dx over x, or u is ln of x plus a constant. But what is u? U is y over x. So y is x ln x plus x, or x of ln x plus a constant. Another example, y prime is equal to 3y squared plus 2xy over 2xy plus x squared, and we can easily see that if we divide everything with x squared, we'll get u everywhere. Let's check that. This is 3y over x squared plus 2y over x 2y over x plus 1, and everything here is a u, so y prime is nothing more than u prime x plus u is equal to 3 times u squared plus 2u over 2u plus 1, right? And now if we do a little math, we get that x du over dx is going to be 3u squared plus 2u, and multiply that with this guy, so minus 2u squared minus u over 2u plus 1 x du dx is equal to u squared plus u over 2u plus 1, and now we can finally get to a separable equation, right, where we have the integral of 2u plus 1 over u times u plus 1 du is equal to dx over x, right? And like we said before, we have two real roots here. This has a root 0 and this has a root minus 1, so they're both real, and this can be separated like this, over u times u plus 1 is going to be a over u plus b over u plus 1. Now we'll do the math. Au plus a plus bu is equal to 2u plus 1, meaning that a is 1 and b is also 1, because u times a plus b is going to be 2, and this is 1, so b is also 1. So this can be separated to 1 over u plus 1 over u plus 1 of du is equal to dx over x. This is ln of u, and this is ln of u plus 1 equal ln of x plus a constant, meaning that finally what we have is that ln of u times u plus 1 is equal to say times x. No, this is without the logarithm, and this is our solution, because if we use the fact that u is y over x over here, we're going to get finally y squared plus xy is equal to x to the third, written in its implicit form, which we don't really care for. I think that's it for now. We will move on on our next video, taking a very important aspect of differential equations, which is the general linear first order ODE, which has an exact solution, and we're going to check what that is. Thank you all, and thank you for watching.